And I also knew him from TASI, so I'm very happy that's here today.
But different generations, though.
Yeah, just a few years apart. But please go.
Thank you. It's a really great pleasure to be here. So I will talk about searches for new physics at the LHC. I'm a theorist, but I'll show you a few slides with data as well. So this is work done with Robert Harris, who's a CMS member at Fermilab, and Josh Isaacson, he's a postdoc theorist, and also with Jan Bike, who's a professor at the University of Wisconsin. And I will talk about two related topics. One is with scalars and new vector-like quarks. The other one is about new gauge bosons. I have a question. Can the experimentalists in the room raise a hand so I know what to expect? Okay. Don't be shy to stop us. We TOS tend to speak our own language, and we can translate it if we are told. Okay. So there are one of the LHC which ended in 2015. And run two that started since then were extremely successful in proving that the standard model is right, up to the limits that have been set so far. The Higgs boson has been measured with high precision in many, many different channels, and we know much more now than we knew before the LHC started. It's important to remember that the LHC is proving directly the laws of nature at the shortest possible distances, and therefore we have no clue what will be discovered or what will be found at the LHC starting from now on. This is a very data-driven environment. Once the standard model Higgs boson was confirmed to have properties consistent with the standard model with some accuracy, we theorists don't have a very clear thing to say. We know for sure there must be supersymmetry or there must be something else. So it's the experimentalists who will tell us what's there. And it's important to remember that there could be all sorts of surprises. Whether it's standard model or it's some other theory that is going to be uncovered, we really don't know. So let me talk then about this class of searches which are quite generic. If you have a new particle that couples to quarks, then this particle can be produced in proton-proton collisions, singly produced, which gives you a large cross-section. You have a resonant enhancement of that production. And since it couples to quarks, it can always go back to quarks. And therefore, the signature is a pair of hadronic jets, which reconstruct a peak. If you plot the number of events as a function of the invariant mass of the event, you find a peak near the mass of the object. So this is very generic. Anything that can be produced can also go back to jets, and therefore searches for pairs of jets are quite important and generic. The problem is that you have a large background, because QCD can also do this, produce a pair of jets. However, if the mass of this is large enough, and if the couplings are also large enough, then you're going to see over a smoothly falling background, you're going to see some resonance, and therefore there is potential for discovery. So having said these generic things, let me now dive into a particular kind of model, which I'm choosing for a specific purpose. I'm trying to answer how far can the searches at the LHC go in searching for new particles of higher and higher masses. You know, when the LHC was first proposed, it was said that this is to explore the TeV scale. And the idea was that we don't know the laws of physics at the TeV scale, 1 TeV. But what I'll show you is that actually the LHC can go way, way beyond 1 TeV. depending on what particles you're looking for. Of course, the Higgs boson is at 125 GeV, which is way below 1 GeV. But now I'm concerned with the hypothetical new particles that can be significantly heavier than the TeV scale. And for that, you have to think of how much content in the proton you have for different particles, for the up quark, the down quark, the anti-quarks, and the gluon. And you find that by far the largest one is the up quark. Well, up quark is about, at least in the regime we are talking about, it's about twice as much as the down quark, and an order of magnitude larger than the anti-quarks. So, as opposed to the Z prime that I showed you on the previous slide that was really coupled to a quark-anti-quark pair, I'm now talking of a particle which couples to two quarks, not to a quark-anti-quark. So this is very unusual. This is exotic, new kind of particle. So I'm talking about a scalar, spin 0, that couples to upright, upright. So I take the right-handed fields here because if you instead talk about the left-handed ones, these are doublet under issue 2, and then you have to worry about flavor-changing neutral currents. If you couple to first generation, you should also couple to second generation and third generation, and then the CKM matrix will make things very difficult. So I'm sticking to the simplest thing that doesn't cause headaches, the right-handed quarks. And here I have a coupling, which is a dimensionless parameter. I put a 1/2 because that's conventional. When you have two fields of the same kind, you put a symmetry factor in there. So order 1 coupling is a normal Yukawa strength here, if you like. If you think about the top quark, the Yukawa coupling to the Higgs is very close to 1. We don't know why it's so close to 1, but order 1 is something typical. If you go way above 1, then this is becoming strongly coupled, and you don't know exactly what you're doing there. If you make it much smaller, then the production cross-section, of course, becomes small.
So your S is a triplet.
Aha, there are 2 options. One is that this carries the triplet, the color of triplet, or better said, yes, a triplet plus a triplet plus a triplet has a singlet in them. Yeah, however, in that case,
generation, 2 different generations.
In that case, Bhaskar is right. This would vanish because the couplings of triplets come with an anti-symmetric tensor that would vanish. So then I have the even better alternative of making this a sextet under the 6 of SU3 color. And that's in the symmetric representation, there is no problem with the vanishing. And on top of that, the cross-section is even larger because the color factors help. So I should have said maybe what are the quantum numbers of the subject under SU3 color times SU2 weak times U1 hypercharge. This be transformed as the 6. Actually, written this way, it should be 6 bar. Under SU2 is a singlet, and under hypercharge is hypercharge 4/3. Since it couples to up quarks, it has to have electric charge 4/3. So that's it. That's the theory. That's the interaction I care about. I can write similar interaction to the charm or top, but I can easily throw those away by having a flavor symmetry acting on the up quark. Once I have this coupling, there is a decay of the diquark scalar into 2 up quarks, and you can compute that. And what's interesting is that even when the coupling here is larger than 1, let's say it's 2, you still have a narrow resonance. The width of this scalar divided by its mass, it's 4% for a coupling of 2. If you go at larger couplings, then this is no longer a narrow resonance. The searches are harder. You know, if you see on the tail of the distribution some increase in overall increase without seeing a resonant feature, you are going to think that provided you don't know what are the Parton distribution functions or something else is wrong, it's hard to establish the discovery of an object. Not impossible, but hard. So I will stick to an upper limit of about that, which allows me to do the narrow width approximation, which says the following, that once you produce the particle, it's really there, it stays for a while, even though a very little while, and then it decays, as opposed to the case where you have an off-shell particle. If it's on-shell, then you have this resonance structure in the data that is quite appealing. So this is large enough and yet self-consistent for doing this narrow width approximation. Are there any questions?
So do you have any other motivation? Since this is a baryon number value, so you see, unless you put something to this.
You don't have to call it baryon number violating. This has baryon number 1/3. 1/3 gives this minus 2/3, and I'm not violating anything.
No, so that's why that means your S is has a baryon number.
Right.
So
But you see, coming back to your question about triplets, if you could couple a triplet to a mu and a d, but then you have this issue that if you couple to those, you can also couple them to a quark and a lepton, and then these two proton decay. So here I don't have to worry about anything.
So actually one time we worked with another way, so SDC, no, same thing.
Yeah.
It's like a DR.
I see. You should show me that paper, because I'd be interested. We thought about that coupling as well, but of course you have smaller content of down quark in the proton, exactly. And that's why I'm not showing.
No, but it has another motivation to do baryon genesis.
I see. Yeah. So you see, I spent lots of time in the past on theories which are well motivated. By what is well motivated, though, it's hard to be very precise. And these days, I think it's good to try to be as model independent as possible. But if you really care about underlying theories with special new principles, this is part of the 126 representation of SO10, which is something that many people like very much because you can model it.
Quarks. So you have a
Right. But as I said, I prefer to be free of prejudice. Here, once they discover something like that, we will all be busy finding those underlying grand principles. Okay. So once I have this particle, I can compute a production cross-section. So this is an integral over the content of up quark in one proton times the content of up quark in the other proton, such that together they have the right energy to produce this thing in the S channel. And you see, of course, it's proportional to the coupling squared. And here's the result. There are various things I should tell you about this plot, but again, this is production cross-section for singly producing one S scalar as a function of its mass in TeV. And this is for the 14 TeV LHC. You can do the same for the 13 TeV one, and you find a smaller cross-section, of course. It's done for, I just normalized the coupling to be 1, but if you want to be 2, make these things 4 times bigger. It's hard to have a larger cross-section than that. What are these things? Well, it turns out that we don't know exactly how much up quark is in the proton. We know a lot about that at scales which we probe all the time, like near the Z mass or near the top quark mass. However, once you go at several TeV, you don't really know very well the Parton distribution functions. So what you do fits at low energy, and then you extrapolate. So they come with a band, with an error band, which is this yellowish thing here. So this is done for the so-called MMHT parametrization of the Parton distribution functions, and this is done for the CTEC ones, and that's what it is. There is some uncertainty in here. but it's not too uncertain not to extract some information from it. Okay, you can do a similar exercise for the QCD background. That's how often do two jets are produced with a large transverse momentum, so that together they have an invariant mass given by a certain value here. And you find that if you integrate over a mass window given by the resolution of the experiment, you find that the cross-section is smaller than this by about an order of magnitude. So we are really, once we get into these very large masses, which is what I call the ultra-heavy regime, you no longer have to worry about the background. Isn't it nice? This is the hardest part, comparing your experimental results with the standard model background, and I'm saying the standard model background sort of goes away once you are in this region. And you can ask how high mass you can get in probing a particle like that in the high luminosity run of the LHC. That is supposed to include about 3,000 inverse femtobarns of data. So multiply this by the cross-section. Here you find that you're going to have several events already at 11 TeV. And since there is no background, imagine suddenly seeing several 11 TeV dijet events. You're going to know there is some new particle there. So I must say, maybe I'm not sure if this is surprising for everybody, but for me it was. I thought, right now searches are done at 3 TeV, 4 TeV, that regime, and it's considered exponentially harder to get here. However, the reason you get so good at this is because you couple to quarks instead of quark and non-quark, where you have much smaller PDFs.
Also, it's a sextet, right? You are winning by the sextet number.
This is a debatable statement. It's probably true. The issue is the following. If you have a different model, like the one you mentioned with down quarks, you have to go back here and compute the width. And if you say, I don't want the width larger than a certain amount, then being a sextet also gives you a larger number here. So in other words,
So you are saying, I see.
Right.
So the resonance, narrow resonance versus the cross section. So they
Right. For a given coupling is exactly true the way you said it, that it's a large cross section because it's a sextet. The Krebs-Gordon coefficients are larger for a higher representation like the 6. But they are larger in the decay as well. So.
But the QCD background can scatter sextets. Sextet initial states in the T and U chain. So.
Right. No. So there is.
So it has access to that combination as well.
Yeah. It's just you don't have the resonant enhancement. So
Yes.
so the main background comes from actually a U quark with a gluon here. So they can be in the 6 representation, and you have the same PDFs, but you don't have the S channel enhancement. That's why it's not so important to look at the background. Although we did look at it. Okay. Good. So from now on, whoever tells you that the TV express the TV scale, tell them that you can go even beyond 10 TV, and they will not believe you, but that's a good discussion they can follow. Now, maybe that's a good moment for me to share some data, just as a teaser. But are there any other questions?
For Bogdan, so intuitively, how, because usually for any machine like a photon or like starting from Dobrescu to this, so we always tend to understand like if it's a 14 TeV, you cut it down to 2 TeV center of mass because that's the 1/6 factor. But here you recovered that factor of 6. So intuitively, how do we?
You know, the thing is, this is an awfully small cross section. Usually people use the picobarn unit for cross section. This is 10 to the minus 6 picobarns.
See, background is so gone, so that's why you can.
It's
so
gone because you're at a huge mass. And what I'm trying to say, this is quite a lot of data. I mean, if you have a little amount of data like we have now, you shouldn't see anything, right? Not even one event. But yes, it goes somewhat contrary to the usual intuition. If you look at all searches for new physics, they stop usually at 3, 4, maybe 60 if collaborations are more generous. Right? Correct me if I'm wrong. I don't want to say things about CMS which are contrary to what the CMS experimenters think. Okay. Can I ask who are the graduate students in the audience? Just to make sure. So you guys should not be shy. Ask us questions, because otherwise we dump at you more and more information with more and more jargon. Any small question is good here. Okay? So don't hesitate. Okay. So let me. Actually, instead of showing you data, let me tell you something about the different type of particle, and then I'll put them together. Okay. So far I talked about the scalar Hall large production cross-section. Let me now talk about vector-like quarks. So, you know, all the standard model quarks have the property that they transform differently under SU2. In other words, the left-handed standard model quarks are doublets, the right-handed standard model quarks are singlets, which means that they cannot get a mass other than by talking to the Higgs. If you have a vector-like quark, that means the left and right-handed components have exactly the same charges, and therefore they can have a mass which is larger than the electroweak scale without paying any penalty, essentially. And they don't need to talk to the Higgs. That's quite profound if you think about it. It's a new type of it's a new form of matter, and if something like that will be discovered, imagine all those articles in New York Times saying that Higgs is the thing that gives mass to everybody. Well, those would be different. They would not get mass from the Higgs. So let me talk about, just to be specific, about a vector-like quark, which is a triplet under color. It's an SU2 singlet and has electric charge 2/3 or hypercharge. In other words, it has exactly the same quantum number as the right-handed up or right-handed top. And these are in all sorts of composite Higgs models. They are motivated, but again, I'm not going to try to talk about grand principles. I'm thinking what new particles can be there and what can they do together. Okay, so the usual story about vector quarks, which are, by the way, searched by CMS and Atlas very intensively. These are the flagship searches now that supersymmetry is less obvious to be searched for. They have this property that if they mix with the top quark, let's say this one, then you are going to have mostly decays into a W and a B quark, a Z and a top quark, or a Higgs and a top quark. And these are the three key modes that are being searched for by the collaborations. However, all of them depend on this mixing angle. And this is a free parameter. In the limit where you take the mixing angle to be 0, all these usual, let's say, standard searches for vector-like quarks are gone. You don't have a decay like that. And in that case, if that happens, the mixing to be very small, then you can think about all sorts of exotic decays. These things would be produced, would be relatively stable, and then if you have a highly suppressed interaction that allows them to decay, they will take that route, because there is nothing else they can do. Okay? So this is some work I've done with Felix Yu from University of Mainz, where we looked at various high dimension operators that can allow a vector-like quark to decay. So I have here the language top prime because that's the mixture of top and chi in the case where the mixing is small. Okay, so you can write high dimension operators where the top prime decays to a top and 2 tau particles. And we even have UV completions where those high dimension operators come from a very heavy particle which is integrated out. So this is an example of what vector-like quarks can do. You always pair produce them from this V, and then they have a relatively long lifetime, and then they decay. I'm interested in the case where the decay is still prompt. They don't travel enough so you can see a displaced vertex. So there are also decays. Now you can write other papers. For instance, Chi with 3 standard model quarks. Then you are going to have decays instead of taus here. Just you're going to have tops and bottom quarks. Or if you couple to the first generation, you're going to have up and down quarks in the final state. So only jets in the final state is a possibility, and actually that's a way to hide those things, because the usual searches require leptons in the final states. If they couple you just have jets in the final state, the limits are not very strong. So the bottom line from those two slides is that vector-like quarks have a lot of possible decay modes depending on physics at very high scale, beyond what's accessible in the LHC.
So Bogdan,
Yes?
closing loops here, you can get dipole decays that go back into your original channels that you thought were turned off, right?
Yeah, no, so we looked at that. I don't have the plot here. It's not that you can, so once you write this kind of high-dimensional pattern, you break this Z2 symmetry that keeps
Right.
them stable. You induce some mixing. This is an excellent observation. However, that's a subdominant decay mode because it's suppressed not only by, so essentially it's suppressed by the loop. We have in our paper various plots that show you how large it can be. So the decay into exotic states is 80–90%. You cannot get larger than that. You always are going to have a little bit of the others because you induce it, as you say, through those. Very good. So let me go back to the dye-quark story and point out that it's perfect in nature to have a theory where you have some scalar dye-quark, but you also have a vector dye-quark. Again, if you look at higher representations of grand unification, you find that they are there, but I'm not going to go in this direction. What I'm saying, instead of having one new particle, let's assume that you have 2 new particles. After all the supersymmetry searches at CMS and Atlas, assume you have 10 new particles, all to be discovered at once. So I'm not doing something very unusual here. So imagine now you have a UU producing a scalar, huge production cross-section, but now the scalar, instead of going back to UU, it goes back to chi-chi. After all, these things have the same quantum number, so you should have this coupling there. And then chi can do whatever you like, almost. In other words, nature has a choice because there is a symmetry that keeps it stable enough until it decays through some pretty small interruptions. And here I show you the case where at one loop they decay into a gluon and an up quark. In other words, these chi's now don't mix with the top quark, they mix a little bit with the up. Again, that can be a flavor symmetry that does that. So the bottom line is that you have the dye-quark either decaying to UU, or which you cannot prevent because it couples here, or decaying to chi-chi, ending up with 4 jets in the final state. So here are some branching fractions. You have this coupling, the ratio of this coupling to this coupling on this axis, and this is the branching fraction to decay either into standard model quarks or into this new vector-like quarks. In other words, this is a 2-jet decay and this is the 4-jet decay. And you see, depending what's this ratio, you can have this decay dominate or not, but you can never make this one completely negligible. There is one other parameter here, the ratio of the mass of this to the mass of that. So you see, if depending whether you pick this one, you get the dotted lines. If you have a larger mass ratio, then you have the solid lines. Again, model very simple. I have 2 new particles with 2 new masses and 2 new couplings. And now, of course, the width is a little bit larger because you can decay in either of them. So for different values of this new coupling, you see you can still be within 7%, which is still a good way to do the narrow width approximation. So I'm not changing dramatically what I showed you before. But that means that not just two jets at 11 TeV can show up by the end of the LHC. You can have, let's say, two pairs of jets, right? Let's say this is much heavier than that, then the two guys are pretty boosted, and when they decay, the two jets are not too far from each other, so you have this topology. Of course, if the mass is closer to half of that, then the jets are going to fly all over the place. But the more jets you have in the final state, the smaller is the background. So you can start thinking about seeing something like that earlier. You don't have to wait to the very end of the LHC to see something where the background is no longer important. Any questions?
Have you thought about using the jet-sum structure analyses for using those very close together cases?
Yes, very good. This is a very active research field, and yes, we are thinking this is actually a case where the background dies even faster when this is much lighter than that. These two are close to each other, but if they're not really overlapping, then that's a place where TCD has a hard time producing. Very good. Okay, so now maybe, is this the right time to show you the data? Let me try. Okay. So you see, the motivation I have is what if? What if there is a new particle? What if there are two new particles? How heavy can they be? If I just learned that there is no diquark, I'll be still happy. If there is one, I'll be even happier. But it's worth comparing what the data sees so far, just to know where we are. So you see, this is the invariant mass of the two jets. And this is the number of events from an Atlas search of last year. And you see, you have lots of data, lots of events here, thousands of events, that masses which are not so large. But once you get to 7, 8 TeV, suddenly you no longer have events to make. Except there are two events here at 8 TeV. Now, when you see events at 2 TeV, people like me go berserk. That's amazing. However, the experimentalists are wiser than us, and they tell us, don't be so excited. After all, you have two protons coming with a total energy of 13 TeV together. If they just graze each other, you're going to have some events close to 13 TeV, which are not too far from the z-axis, right? So it's not so unheard of. What's special about that is, however, that these are at very large angles. So you have the two protons coming this way, and this fly almost perpendicular to the beam. And that's much harder to have. You have to have in those partons, in other words, those quarks inside the proton that collide, to have almost the whole energy of the proton, and the other quarks and gluons to have very, very little. So that's why it's such a rare thing. On the other hand, the background is not negligible. You see, I was talking on the previous slide about 3,000 inverse femtobarns. Here they have only 37, so it's 100 times less data than by the end of the LHC. So there is a little bit of background. Nevertheless, the background is significantly smaller. So two events are sort of interesting, but not big deal. Maybe what's more interesting is that there is a gap here. That the previous events are at around 7 TeV, and then there is nothing else, and then suddenly two of them. But we've seen that in lots of other experiments. The ice cube. What were the names of those? Those people are more imaginative than the LHC experimenters. They gave names to those events. Ernie and Bert. Right? We should come up with names for this. It turns out when Ernie and Bert in Ice Cube came out, which was something similar. There was a gap, and then suddenly two events near each other. We were all in awe, except since then the background slowly caught up with them and filled the gap. So there are all sorts of fluctuations that can happen. This is not a big deal. Okay. Let me show you the CMS search. This is done with about twice as much data because it came out in August this year. This is the data, the black points. You can ignore these slides. These are various other things I can tell you about. So you look here, and suddenly around, since there's more data, indeed there are events up to 7.5 TeV. And then again there is a gap, but suddenly 2 more events. It's probably hard for you to see, but this is 1 event, this is 2 events. And where are these 2 events? Also at 10 TeV. So now you have to come up with 4 names for these 4 events. On the other hand, the background is larger because there's more data. So yes, 4 events in the 7.9 to 8.1 TeV range. But if you look at the background, now that's a tricky part. How do you count the background? Because when you say what's the background, you have to say what's the mass window where you look at. So our experimental colleagues tell us that the resolution is around 4% for jets at very high mass. Is that a good number? Whoever is in CMS, correct me if I'm saying things that might not fit what you know. So 4% means I cannot take just a small window like that. I should take a window which is a bit larger, about 600 GeV, right? Because the resolution is on one side, if I understand correctly, so you have to take twice the resolution. In other words, 8% of 8,000, that's more like 600 something GeV. So in this thing, I start adding up the background from these beams, which is higher than the ones here, and I end up with 1.5 events. So a prediction that a background of 1.5 events fluctuates into 4 events is not such a rare thing. It happens often. So maybe one should not be too excited. Maybe we don't need to give them names. However, it's a thing that is worth keeping an eye on. If more 8 TeV events appear, then we should start being more enthusiastic about it. Okay?
But it'll just get harder to come up with names for them.
Yeah. Yeah. I look forward to that situation. Okay. Good. Now, that's not the whole story, though. Let me talk about these 2 events. CMS has done something very nice in their latest paper on dijet searches. They showed us the event displays, which is really what the jets have done, which is not too often that you see in the experimental papers. And here's one of the 8 TeV events from CMS. When you see it, you should probably assume that I did something wrong. How is this a 2-jet event? It turns out that I didn't do anything wrong. This is the display from the latest CMS paper. So the explanation is the following. CMS is trying to be very careful. So they look for the case where indeed you have the protons coming this way and you have some jets running in a pretty central region here, transverse to the beam. But what they do, so first they ask a certain cone size here to have to be the jet. To be more precise, this is what is called an AK4 jet, which means a certain angle opening between a certain opening for the cone where they look for jets. A jet is a collection of many particles that hits the hadronic calorimeter. So you have to say how large is the area where you look. But once they do that, what they do, they look in a larger region. To be more precise, there is a quantity that some of you probably know what it is, delta R to be less than 0.4. That's the meaning. And delta R is more or less an angular separation between these points. But then they take a much larger region, which is delta R less than 1.1, just because they say in this, for a jet like that, probably there is some additional radiation, some additional gluons that come here, and if you don't include those, you're going to underestimate the momentum or the energy of the deposition in the hadronic calorimeter. So that's exactly what they do. They take the highest PT, highest transverse momentum jets, which are, let's see, this one, 2 TeV PT, you see, and this one, another 2 TeV. And then they write this, they make this larger cone around them and include all the radiation. So doing that, they captured 2 extra jets in here. That was not exactly what they were planning to, because the idea was that perhaps there's a lot of little junk here, additional jet activity near the very high PT jet. But the algorithm was not designed to veto on that, so when they looked at their highest PT jet, they found this very unusual topology. Okay? So now, to people like me, this looks like really a 4-jet particle, sorry, 4-jet signal that sounds a little bit like what I showed you before, right? If you remember. You have an S-channel resonance, you produce 2 particles, each of them decays to 2 jets, you see 4 jets in the final state, right? So that's pretty unusual, but if it's new physics, it's easy to explain. Can it be QCD? Yes, there is a statement that anything you can see can be QCD. There is a non-zero probability for QCD to mimic your event. The question is, how small is that probability? And we are trying now to compute a QCD background to this. What's the probability for producing an event like that? We find a very small number, but we are still working on it, so you don't need to know how small it is. There is a generic statement, never be excited by one event. I mean, yes, even if the probability is 1 in a trillion, well, maybe it just happened once. It happened in our lifetime, right? Until you see more, you cannot assign credible probabilities to one event, right? So I will not claim anything based on that, and nobody should. It's just a peculiar thing. However, we should pay attention, right? So we have a very special kind of 8 TeV event. Now, how are the other events? Well, CMS is kind enough to show us the other 8 TeV event, which is 7.9. You see 7.9 TeV. That looks like a real 2-jet event, right? And by the way, Atlas doesn't do this fancy stuff that CMS is doing. They just look for narrow jets, and therefore those 2 events from Atlas are more like that than like the other one.
Bogdan, is there any chance that this could be a double Cartan scatter?
Yeah, there is a chance, but it's tiny. You ask how often it happens to have something like that.
Really hard things.
This is about 1 in a trillion. You have to square it there. It's much more likely to have a background from something like that, where you radiate a gluon that splits into 2 gluons. You see, that's the main background. But
It's just weird that they
is
sort of
pretty small.
seem almost like they're 2 back-to-back pairs that are balanced in PT.
Right. Yeah. No, but the double parton is really small probability. It's much larger probability to have a 4-jet event like that, where it just happens that their orientation is like back-to-back, as you say. Okay. And that's not the only diagram. We came up with about 20 different diagrams that do it. It's always U initial state, that's 2 extra gluons in the final state that gives you the largest contribution. In any case, I'm not saying one should be enthusiastic for now, but keep an eye on it. If you are going to see more 8 TeV events, that would be nice. Also, Atlas should do a search that mimics what CMS is doing, because perhaps, who knows, maybe there are more of those strange events. Okay, so that was my part about data. Are there any questions? Okay. Good, so then I'm ready. Take it as a teaser for now, something worth paying attention to. So let me now switch gears and talk about a different kind of theory that doesn't have either the diquark or the vector diquark in it. Because I'm interested also in asking the question, can there be new gauge bosons which are very heavy? After all, the things that are producing the S channel with a large cross-section right now are the Z and the W. Can there be something similar at very high mass? Now, you see, for something like a Z prime, you cannot have large couplings because Z prime is associated with a U1 gauge symmetry usually, and doesn't have asymptotic freedom. So the coupling has to be small, and then you have to embed it into a larger structure to be well behaved at very high energies. However, there is a certain extension of QCD. Instead of having one SU3 group, you now have two. So you just embed the QCD gauge group into a slightly larger gauge group here. What does it imply? This has to be spontaneously broken to this one. One particle left over is the gluon, which is massless, but then you have an additional linear combination of the gauge bosons from here, which is essentially a gluon prime. In other words, a heavy gluon. However, people call it a long time ago coloron, so I'll go with this name here. Okay? So this is a spin 1 particle, which is a coloron. And the nice thing about this embedding is that you can give it a large coupling, as large as the gluon coupling to quarks, and not worry that it would blow up in the ultraviolet because this has asymptotic freedom. At higher energies, it becomes smaller and smaller. Okay, and then you have, instead of one gauge coupling, you have two. From these two gauge couplings, you can find, for instance, how strongly the gluon couples, G strong. And also you can find out how much the coloron couples to quarks, which is essentially the same coupling as the gluon, except you have an overall normalization, which is given by the ratio of the two gauge couplings. So you have one new free parameter. If tangent theta equals 1, then the gluon prime or coloron has exactly the same coupling as the gluon, which is a pretty large coupling. Now, you have a larger gauge group, you have to break it. So you need a larger scalar sector, the Higgs sector of QCD, if you like. Except you get more particles this time, because to break the SU3 times SU3 gauge group, you need a scalar that transforms under both of them. I call this sigma. So sigma is a triplet under one SU3 and an anti-triplet under the other one. So you can work out what's left of this scalar once it acquires a vacuum expectation value. So this is equivalent to the symmetry breaking scale. You end up with one color octet. So theta is a color octet scalar, and you also have two color singlet scalars. It turns out that this is not very important. It doesn't do much, but this one it is. So the Higgs sector of this theory has these two particles, at least, if you don't count this one. And you can work out the theory. You find some interactions. There is an interaction of the coloron with two thetas, which means that you can have one coloron decaying to two thetas, if they are light enough. Or you could also have an interaction of the coloron with one theta and one phi. Okay? So you have two different decay modes for this coloron into scalars, with the only condition that the masses of the scalars are less than half the coloron mass. There is an upper limit of how heavy the scalars is. It's similar to why the searches for Higgs didn't have to look at very high mass. But it's not absolutely necessary that they are below half the coloron mass. So this is maybe half of the parameter space. So looking at the coloron branching fraction, you can have decays of the coloron into two jets. The way you produce the coloron from coupling to a quark and an anti-quark, it can go back into a quark and an anti-quark. Or else it can decay to thetas, or it can decay to a theta and phi. And you see, depending on the parameters you can have here, the decays into this can dominate. So now, essentially, I'm not sure if I have a diagram later on. Let me draw it for you here. So QQ bar going to a coloron, going to theta, theta, and then what is theta doing? Well, at one loop it decays to two gluons. Okay. So you see, as opposed to the theory that I discussed before, where I put in by hand the diquark and the vectoid quark, I still have a similar topology now, except these particles are now close friends. Think of the stellar model where once you have the Z, you also need the Higgs boson. That's the similar thing. So I'm doing only one thing. I'm breaking a larger gauge symmetry, so then I need all these particles, and I end up with a 4-jet final state as well.
What is, this was long-lived. How does it look inside your hadronic calorimeter?
Sorry, theta has to be long-lived?
Any of your color, produce a color on it.
So in the previous model where I had vectoid quarks, those can be very long-lived. And then you can have displaced vertices. If the decays are before the hadronic calorimeter, it doesn't make too much difference, except you are not going to see some tracks in your detector. Here, this cannot be too long-lived, these status. They decay at one loop into two gluons, and this is fast enough so you don't have to worry. But I'll say something about displaced vertices. That's what you're thinking about, long-lived particles, right? I might say something a bit later about that. Are there any questions? Okay, so now you have some limits from digest searches for colorant decaying directly into quark anti-quark. They exclude large values of tangent theta, especially for smaller values of the mass. So you have to take some constraints into account, but they are not particularly strong. And the reason is that final states with jets have a background in masses which are small. And this is a story about how theta can decay. I showed you here one possibility. Theta decaying to two gluons. If the other scalar phi is lighter than theta, then you can have theta decaying to phi and an off-shell coloron. So this is really a three-body decay with the coloron then going to jets. So you can have this decay to two jets and one phi, which
The mass of this phi should be
it's a free parameter. As long as phi is lighter than theta, and theta is lighter than half the gluon prime mass. So if this is 7 TeV, this has to be below about 3 TeV, and this has to be below 3 TeV.
But that has to come from the same scalar potential of Briggs minus U3 squared. And
Right.
So does the mass of the theta.
Yeah, so we have full expressions for the masses as a function of the couplings, and there is plenty of freedom. Actually, there is a certain symmetry under which this one can be massless, essentially, except you have constraints from experiment. But this can be a Goldstone boson of the potential. Very good point, though. Okay. So, what can phi do? You see, one story, you might be wondering, what am I trying to say? The point here is that I'm writing a very simple theory, a gauge extension of QCD. Instead of one group, two groups. I have to break that, then I have a whole, lots of processes to worry about. In other words, the phenomenology is very rich, even though I'm doing essentially one thing to start with. So I have, besides the coloron, I have two particles. If theta now decays this way, then what is phi doing? It turns out that phi cannot decay very easily. The simplest diagram we can come up with is this one. It's a 3-loop decay. And the reason is that you have to break CP somehow. So you have to couple to quarks in the end and to have a weak interaction at the other end. So this phi is pretty long-lived. It's a 3-body decay. And think about this kind of diagram. You produce two thetas, each of them decays to phis plus jets, and then what is phi doing decaying, let's say, to two W's, or to Z gamma. So you end up with an amazing event in your detector. 4 jets, which are prompt, plus a W pair, and a Z and a gamma, which might be somewhat displaced. This is very, very peculiar, and yet the theory you start with is very simple. Okay? And we have here cross sections and all sorts of things. So I think the bottom line is that theory can be simple and the LHC phenomenology can be very complicated. And furthermore, depending on the mass ordering of these scalars, you can have, for instance, only jets in the final state, lots of jets, which are hard to measure. You have a QCD background. So there are plenty of searches that CMS and Atlas can do for a particle like that. Here's another example where instead of decaying to theta, theta decay to theta phi, so you have fewer jets in the final state. And these are more possible topologies. Maybe I should go to a slide where I have a combination of all these things. Okay, so here are some possibilities. You can decay the color onto theta phi, or it can decay to theta theta. And then theta can decay to phi plus 2 quarks, or theta can decay to 2 gluons. And phi can decay to WW or gamma Z, for instance. So you have all these possibilities. And then, depending on the relative masses of this, so this is a theory with 3 new masses, right? You have the colon, theta and phi, 3 new masses, and one overall coupling this tangent theta that tells you what's the production cross section. So depending on how the masses are arranged, you can have some of these things boosted together in one big object, right? So for instance, look here. This is the case where phi is much lighter than the other things. Then you have some essentially one object which is formed of 2 W's decaying while they go in the same direction, essentially. So that's what I mean by JWW. And this happens when phi is much lighter than that. If you know any graduate students that want to do a new search, none of this has been done, essentially. The only exception is a search for 4 jets at lower masses than what I showed you. Other than that, searches with lots of jets with boosted topologies of various kinds, as far as I know, they have not been done. So, you know, there's a lot of discussion. If the LHC has not found something by now, what's the probability to find it in the near future? Well, it's pretty small because the argument is that the discovery potential grows like square root of luminosity, and that's growing very slowly. However, if a search has not been done at all, then you can have a discovery now on tape and not know about it, because any of this final state is hard to see, unless you do a dedicated search.
Mass of phi is about
It's a free parameter. If it's below about 200 GeV, then it's a displaced vertex, because the decay width becomes smaller and smaller. In other words, the lifetime is smaller. Yeah. So again, this is if it's a decay open. So I'm in the 200 to 1 TeV range, 200 GeV to 1 TeV range for these things to be
since you have a free neutron and particles, you can search phi through the vector Poisson fusion.
Good.
Mass is like.
However, that coupling is pretty small because it's essentially the inverse of that. You have 2 W's and you have all these loops which make the coupling very small. So it's quite different than the Higgs. You're right in principle. But in this case, I think the other cross-section is too small. Maybe I should just conclude here. So it's important to keep in mind that the LHC is exploring the uncharted waters. We should not have biases about what will happen. Try to look at as many final states as possible, and it's nice that there are new techniques being developed about, for instance, jet substructure and all sorts of things that CMS and Atlas are doing. It's quite amazing that you could have some simple model with a new particle that would lead to signals, even if it's as large as 11 TeV. So this sort of opens up a larger range of masses than what I was aware previously. And in this particular model, which is an extension of QCD, you could still have a 4-jet event like the one we've seen. You see the one I wrote here, but it can have many more. So maybe, you know, one possibility, if the 8 TeV event is due to a coloron, you might see all sorts of other 8 TeV events in other searches, which would be quite